Mr. T here with a tutorial on inverse trig functions. This is part of a series of lectures on trigonometry for my Algebra 2 course, and today we're talking about inverse trig functions. Before we get into the trig part, let's talk about what inverse functions are. Inverse functions undo another function. So I've shown here a few simple functions. A linear function here, f of x equals 3x. If we want to undo time multiplying by 3, we divide by 3, so this would be our inverse function. If we're squaring, we square root, and we learned in our chapter on exponential and logarithms, to undo a exponential function, we take the log of that base. You may also remember from earlier in the year when we talked about function notation that if we take the inverse function of a function, if those two functions are inverses, we get x, meaning it undoes the function. Pictorially, what we're talking about there, remember when we talked about functions, they're like machines. So we have a machine called f. It has inputs, and frequently in math, input is represented as f, and a function creates an output through some mathematical operation, and in this case the output many times is called y. Now if we have the inverse function, it undoes, so we're taking the output of the original function and treating that as the input, so now we're going to the other direction on our function. So this y becomes the input to here, it's our x, and it generates or undoes the function, so its output is the original input that we started with. So that's what this notation, this composite function notation, is saying. And when we are talking about trig functions, so if this is a trig function, say sine, this would then be sine inverse. Our inputs are angles, and our output is a ratio. So for the inverse trig functions, our input is a ratio, and the output is an angle. And as shown here, if these are our three primary trig functions, the notation for their inverse uses the superscript -1, just like on the function notation. Well, that wouldn't be theta, that's going to be an x, because the input's not an angle. So would be sine inverse of x, cosine inverse of x, and again tangent inverse of x. Now there is an issue with our trig functions. Let's talk about that on the next slide. And let's go back to our unit circle. And let's say we were using the unit circle trying to evaluate the inverse sine of 1/2. Again, this is asking me what angle has sine of that angle equal to 1/2. Now if we use our unit circle, if we're using the entire unit circle, remember sine is the y-coordinate, so it could be 30 degrees, or it could also be over here, and it could be 150 degrees. Now in terms of functions, that causes a problem because we have a single x value that has two possible outputs, two possible y values. That will violate the definition of a function, and if we drew a sketch, it would violate the vertical line test. So we want the sine inverse to be a function, so to do that we have to limit the possible range of the function. So for sine functions, to get unique values, we restrict the outputs to be in these two quadrants here. And we go positive and negative from 0. So if you use a calculator to do the inverse sine, you're going to get either up to positive 90 or negative 90. You will never get an obtuse angle when we do the inverse sine. By doing that, every value of input, every ratio that we have has a unique output. So it now becomes a function. If we do the same thing with cosine, so let's say what angle gives me a cosine of 1/2. On the unit circle, that's the x-coordinate, so we have here 60 degrees, or down here we have 300 degrees. So we have to avoid being in these two quadrants. So for the cosine, the angles are going to come in this semicircle. So it's going to be between 0 and 180 degrees, or 0 and pi. So again, if we state the range of our trig functions, the inverse sine will be between 90 degrees and negative 90 degrees. And the inverse cosine will always be between 180 degrees and 0 degrees. And again, on radians, this would be between pi over 2 and negative pi over 2, and radians here between 0 and pi. Now this will become a key factor when we are solving trig equations, dealing with this limitation, and also when we are working on something called the law of sines and law of cosines later in this unit. So let's look at some examples of how we might use the inverse trig functions. So our first example will be a right triangle problem. So let me sketch here as best I can a right triangle. And this is, say, angle A, B, and C. And let's say side A is 2 and side B is 4, and we want to solve the triangle, meaning we have to find angle A, angle B, and side C. Now we don't have enough information here. We could find side C by doing the Pythagorean theorem, so that's going to be C squared is going to be 4 squared plus 2 squared, which is 20. So C is going to be the square root of 20, which is 2 radical 5 in radical notation. So we've already found little c. But we don't have enough information here to find the angle. However, we can use the inverse trig function. So let's show how we would figure that out. Let's find angle A, and let's use these two values here. So if we set that up, 2 is opposite and 4 is adjacent. That's the tan function. So the tan of angle A is equal to 2 over 4, which is 1/2. Now we need to solve for A. Now we cannot divide by tan. Tan is not a value. It's a operator. It does something. It acts on angle A. So the way we undo operators is inverse operation. So I need to take the inverse tangent of both sides of the equation. I simplified the 2 fours. Now, from our definition of inverse function notation, if you take the inverse of a function, you get the input. So the inverse here is going to be just angle A. And now let me pull a calculator over. And make sure your calculator is in the right mode, so verify that's in degree mode. And now we can calculate the inverse tan. Those are in yellow, so we need to use the second button. And we can input here 1/2 or 0.5. And we get, we'll round that so we get 26.6 degrees. Now we can find angle B. We could use another inverse trig function, but we know these two angles add to 90, so angle B is going to be 90 degrees minus 26.6 degrees, which is 63.4 degrees for angle B. So now we have found B, A, and C for our problem. Let's look at a trig equation. So let's say we want to solve the equation sine of theta equals negative 0.35. Now you may think that we can just go to our calculator here and put that in, and we can do that. We will get a solution. Oops, that was negative. And we get negative 20.5 degrees. Let's make a coordinate plane here. So one of our answers here is negative 20.5 degrees. And if this is the unit circle or radius of 1 here, the y-coordinate of this point would be 0.35 or negative 0.35. But is this the only solution? And the answer is no, because if we go straight across here, we will have another point on the unit circle that has a y value of negative 0.35. And this angle would be the same angle here, so as a reference angle, this is 20.5. So our two solutions on the unit circle for this trig equation is, or would be here, 180 plus 20.5, which would be 200.5. And the other one would be around to here, so that's 360 minus 20.5, which would be 339.5 degrees. And these are not the only solutions, because for each of these angles we could do all of the coterminal angles for each spot. So we could add multiples of 360 degrees and multiples of 360 degrees here. So if we were trying to find all the solutions, there would be an infinite number of solutions. Now frequently when we solve these problems, it will be worded as solve sine of theta equals negative 0.35, and it might say for theta in the third quadrant, or it might say for theta between 270 degrees and 180 degrees. If we solve the problem worded this way, which is the way a number of the problems in your book are going to be worded, when we do the calculator here, our angle that we get, so our, let me call it like a sort of like a reference angle, that is a solution, but it's not, it does not meet the criteria of this solution that we were looking for here. So we have to go to the unit circle like we just did a minute ago, and we can sketch in the calculator solution, where this is 20.5. But we need in this angle, this quadrant over here. So we have to draw, we treat this, if we take the absolute value of this, we treat that as a reference angle. We just talked about reference angles. Sketch that in there and then find this angle. So our answer here, the solution for this problem, theta is going to be 180 plus the 20.5, or 200.5 degrees. So if it doesn't give you a restriction, then you kind of need to assume that you have an infinite number of answers, and we write it in the form of all the possible angles one time around the unit circle and then multiples of 360, where n represents any integer. Or again, we could have a problem where it's restricted like here. So this is an introduction of inverse trig functions, and we'll be using those going forward in our lessons.